Learn here only two things. We will learn about how to fit experimental data and produce very nice correlation between measured data and fitted data. And then we're going to learn about a concept of structures, which is like a class in the language of C and C++. And the structure is a way to organize our data. So let's first look at fitting data. So fitting data, we see that we could use a Matlab code to write the vector x. It's a row vector for the temperature, and the vector y, which is another corresponding row vector for the thermal conductivity of copper. And then I'm going to use a polynomial fit with degree 3. So it's a cubic polynomial. Then I use the command polyfit. So before we go there, here's the structure for polyfit command. It operates on the independent variable is x, the dependent variable is y, and it fits the dependent variable with an order of a polynomial n. The result is stored in a vector p, and p is a vector of numbers that are the coefficients of the polynomial. Notice that if you have a polynomial n, then you have n plus 1 coefficients, because if you have a second order, it would be a0 plus a1. Let's say we can write it in the same order as Matlab. So we would have the highest order would be a1 x squared, and then we have a2 x, and then we have a3, which is a free parameter, and this is a second order polynomial in x. So it's the second order, therefore you have 3 coefficients. So these 3 coefficients are your vector p. So p are the coefficients. So moving on, we'll see that the result of the fit are obtained in this vector of coefficients p with some other parameters that we're not concerned with at this point. But basically, once we get p, then the problem is solved, because we can reconstruct the polynomial from the coefficients. There's a couple of functions that go with that, and first one is the roots. So if you have the vector here, they call it q, which is the same as p, of the coefficients. Transpose, it means it's a column vector. Then if you use the function roots of q, then it gives you the roots of the polynomial. If it is a second order, it has 2 roots, third order, it has 3 roots, and so on. If you have the roots, you can reformulate the polynomial backwards by saying q is equal to poly of r. So usually we just worry about the coefficients vector q or p. So once we have this q or p, then we can evaluate the polynomial, with this function polyval. So this is an evaluation function. The input to this function are the members of the vector q. These are the members here of the coefficients, and you evaluate it at a value of x, an independent variable x. So x could be a scalar. If you input a scalar, then you will get y will be a scalar. If x is a vector of values, then y will be also a vector of values. And that will be a nice way to evaluate the function at any input value of the independent variable. So let's see now how this works in this program. First, we use polyfit to produce the coefficients. The coefficients p, if you write them down, they will be if n is 3, then p should be 4 coefficients. So it would be a vector of 4. So it would be p would be like something here, something here, something here, something here. That's the p vector that we would have. And once we have p, then we could use it. All right. So first thing is that we want to evaluate using the p. So evaluate where? Well, we can generate an entire vector with linear space command, lin space, from 70 to 300 with increment of 10, and the result will be at a xi is a new vector. And then if we put in that new vector xi into the polyval, it produces yi, which is something new that is actually fitted in that case. And once we have the yi, then we could plot x and y, and with an open circle. This is an open circle. B is blue. So that's the characteristics here. And we also can superimpose the fitted vector, two vectors, which is xi and yi. These are this x versus yi. But now when we plot them with a solid line. This dash is solid line, and B is black or blue in this case. Sorry, blue in this case. Black is K. And we got the result. So in this case, we are able to do the evaluation. So let me show you a snippet of a code. So we go back here, and our code is based, here is the vector x, here is the y. So forget about this part because we did it before. And let's say we have third order polynomial, then we'll fit x and y to a third order polynomial, n is 3, and we produce the vector of coefficients p, and then we make a new vector xx, or array xx, starting from 70 to 300 with increment of, say, 5. We could even make this 5, so it'd be a very big array. And then we would evaluate yy at every point of this big array with the coefficients that we found. And then we can plot the experimental results versus the fitted results. And here I change it to red. So let me see if I can get to Matlab here, right here, and then let's say if we're gonna run it and then see what happens. So you can see here's what happened is that let's review this first. So what happened is that P is now the coefficients 1, 2, 3, 4. So that's the values of the coefficients in descending order. So it looks like the third order is almost 0 here. Is 0 actually, because I don't know if I write it maybe in higher precision, then the 0 could be a small number, which is most likely. And the vector x, the new vector xx is right here, and the new vector yy is right there, which is now the fitted ones. And then I plotted those, and it gives me, well, I notice here that I might have made a mistake because I have 1, 2, 3, 4, 5 points only. So you have, that's why the red line looks jagged, like 1, 2, 3, 4, 5. So I gotta do it again with a higher precision, linear space from 70 to 300 with the number of points here. See, this is all wrong, and I want to get the increment is right here to 70 to 300, and then the number of points, let's say I want to have 100 points, so it'd be very very accurate. So if I run it, then you can see that the line is very, very smooth. The red line is very smooth and very nice. And I get all the information on the screen, the vector y, x, and the p as well. So this is a nice application of this polyfit and polyval idea that we could use in fitting data. The next topic is the topic of structures, and structures are classes like in C, and the class is something that can have let's say CS is a class or a structure that can have many members, and the members, so that we have member 1, member 2, and so on. And each member can be anything. It can be real, it can be complex, it can be text, it can be a vector, it can be a matrix, anything. So in this example, I have CS dot, so you access the members through this dot operator. So when you have CS dot scalar, so this is the variable name, it's called scalar. That's actually CS dot scalar is the variable name, and you input its value by defining it by that line. When you say 2 plus 3i, then you define that it is a scalar. And likewise, when you have CS dot text, and then you put it in quotation marks, then you defined as text. And when you have a complex, when you have a conjugate, then you define it, and then you have a vector like that. This is a special matrix called Hilbert Matrix, 5 by 5, so it is stored like here. And once we type CS, this one single word, it will spit out all of the elements like this, like that, like this, like this, and that's a way to input the data in this format. Another way to organize the structure is to just use the command, the function struct, and then input whatever you want. So separated by commas. So you can input a scalar, and like this is the name followed by the value. Name followed by value, and so on. So either we have the input to the structure in one line, or we could do it member by member, as you could see on the top lines in here. So I think with that we have an idea about how to fit the data and how to construct structures. We will use structures in organizing large data sets, as we'll see in data processing. For example, the structure itself can have an index. So if CS depends on the frequency, as we'll see later, like different frequencies, then I can say CS of, I can make CS itself as a vector. So a vector of structure 1, structure CS1, CS2, CS3, and so on. Each one can have its own members, and therefore we can organize our data a lot better than before. So I think we're going to stop here.